if you've ever done a prob question and you're drawing the tree diagram, maybe a coin flip or something like that, and the tree diagram looks like this. So you got, for a coin flip, heads or tails, heads or tails, heads or tails. So the scenario is that you've got two possible outcomes for the experiment, and for each coin flip, the results of the next coin flip are independent of the previous. Then what you've got is actually what we call a binomial experiment. Okay, so here's how to detect whether you've got one, or also known as a Bernoulli sequence. So if you see the word Bernoulli, it's a binomial experiment. So for any binomial experiment, there's a fixed number of trials, n. So we're doing the trial 10 times or 15 times or 3 times, 3 coin flips. Each trial has 2 possible outcomes. So the minute you draw a tree diagram and it's got 3 or 4 possible outcomes, that means it's not binomial. I can spell. Binomial. Okay, the probability of a success is constant. Okay, so again, success being either heads or tails depending on the experiment. So there it's success, success, and it's always the same probability. Okay, and that basically means that the trials are independent. So the outcome of one trial does not affect the outcome of any other trial. So if we know that that's on, what we can do actually is, instead of drawing tree diagrams, we can actually use this formula here to help us work out the probabilities. And it's much, much faster than trying to sift through the tree diagram to find which branches might match it, particularly if there's a binomial experiment that runs for, say, 7 trials. You imagine the tree diagram for 7 trials. Here's the tree diagram for 3 trials. Okay, here's 4. It's getting pretty complicated. Here's 5. And you can basically see that for a 7 trial experiment, you actually physically won't be able to draw the tree diagrams, let alone try to find the right branches that match kind of the thing that you're after, like success, fail, 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 success, success, fail, 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 etc., etc. So instead of having to draw the tree diagrams, what we do is we get the formula to do all the calculations for us, and it's pretty elegant. So yeah, this one is on the formula sheet, and this one is also on the formula sheet. That's new. So as of 2023, those 2 formulas now appear. Alrighty, so let's get into an example. This. Make sure you define it. So once you've detected that you know you've got a binomial experiment, you need to define it. So we use x and then we use the tilde. We usually use the words by, where n is the number of trials, p is the chance of success. Okay, so here we go. Consider the example where we rolled an ordinary fair 6-sided dice 3 times. We defined the random variable x as the number of 5s rolled, and this was the probabilities calculated when we used a tree diagram. Now, why is it binomial? Because you might think, dice, there's 6 possible outcomes. 1, 2, 3, 4, 5, 6. But actually, in this experiment, all we're looking for is the number of 5s rolled, i.e., did I roll a 5 or did I not roll a 5? Okay, so let's draw what the tree diagram would look like for this experiment. So we're going to go 5 and not 5. What are the chances of rolling a 5? Well, it's 1 in 6 because it's ordinary, and 5 in 6 for not. So it's going to be 5 again and not 5. 5 again and not 5 on the second roll. So that's going to be 1 in 6, 5 in 6, because the rolls are independent. 1 in 6, 5 in 6. And we're doing it 3 times. So we've got 5 or not 5. 5 or not 5. 5 or not 5. 5 or not 5. And 1/6, 5/6, 1/6, 5/6, 1/6, 5/6, 1/6, 5/6. So that would have been the tree diagram that was used to calculate these. And let's just try one out. So we'll try 3 5s. This would be 5, 5, 5. So it'd be 1/6 times 1/6 times 1/6, which is 1 over 216. Okay. No fives would be not 5, not 5, not 5. And you can see 5 times 5 times 5, 125, 6 times 6 times 6, 216. Now these ones here would have been calculated using those formulas. And I might just do one of those in a sec just to show you. But let's put these dot points down. So X is a binomial experiment. Why? All right, well, let's look at the things that have to happen. There is a fixed number of trials. And in this case, it was 3. All right, let's see. Each trial has 2 possible outcomes. 2 outcomes, 5 or not 5. What else? The probability of success is constant. Okay, so constant prob for success, which is 1/6. But that also means that the constant probability for fail is also going to be there, which is 5/6. So the last one therefore means that the trials are independent. All right, so that means we've got the binomial experiment. So let's do 1, okay? So that's going to be, this case, we're going to get either 5, not 5, not 5. That's one of the possibilities. 5, not 5, whoops. Start that again. We're going to get not 5, 5, not 5, or not 5, not 5, and on the last roll we get a 5. So there's 3 possible branches that we were looking for to go and count those probabilities, okay? But why don't we use the formula? Okay, so the formula says that we're going to do n choose x. Okay, so that's the number of trials, which is 3, and we want 1 success. So that's 3 choose 1. Now, funnily enough, that's 3, which matches the number of branches. All right, now what we're going to do is the formula will say that it's the probability of success to the power of 1. That means that we need to see 1 success. That's 1 success, that's 1 success, and that's 1 success. So it's 1/6 to the 1. And then it's going to be 2 fails. So we're going to get a fail and a fail, a fail and a fail, and a fail and a fail there. So that's going to be 5/6 and 2 fails. But the formula says that we just do 3 take away 1, which is 2. And that's how we work out these ones here. So maybe by yourself, try to see if you can work out how 15 over 216 was evaluated. All right, so let's do a couple of questions. So we've got a new drug is known to cure a certain illness in 40% of cases. 10 patients take part in the testing of the drug with a chance of being cured in each case independent of the previous. I added that to the notes only because VCAR tend to use this sentence in binomial questions, and that's the big thing that I look for to detect whether we've got binomial on our hands or not. So find the probability correct to 4 decimal places that 4 patients are cured. Okay, so before you go anywhere else, make sure you define your distribution. So first of all, let's say that let x equal the number of cures. Okay, so that's what our random variable is. And how many times are we doing this? We're doing it 10 times, so we've got 10 patients. And the chance of success in this case is curing the illness is 0.4 or 4/10 or whatever. Okay, so this one here, we're looking for exactly 4 patients being cured. Now again, hopefully you can see why we're not going to draw a tree diagram for this, because you're going to have first branch, second branch, third branch, and I'm already running out of room to do it. So we can't do 10 branches, and I'm certainly not going to count up the number of branches. So we got that. Now what I'm going to do, I'm going to do this 2 ways. I'm going to show you how to do this with the formula, and then I'm going to show you how to do this with the calculator. So equals 4. So we're going to do 10 choose 4. Then it's going to be success, which is 0.4 to the power of 4, because we're going to see 4 successes, and this is going to count the number of branches, 10 choose 4, whatever that is. And then 0.6, we're going to see out of the 10 trials, we're going to see 6 fails or 6 not cures. So that's going to be that one there. So we can get the exact answer for this rather than rounding. Even though this one says round, we're going to get the fraction, I think. Okay, so we're going to use NCR. So just recall that NCR is here, combinations. And we go 10, 4. Then we're going to multiply that by 2 on 5 to the power of 4. So 2/5 to the power of 4. Times, what's that, 6/10, 3/5 to, oh yeah, 3/5, of course it is, to the power of 6. So there's our exact answer. All right, so 4,89888 over 1953125. So to 4 decimal places, that's going to be this number here, 0.2508. Now what I'm going to do is just show you the way we can do this with the calculator, not having to use the formula. So the calculator has got inbuilt distributions, which you would have seen last year, and this one, Binomial PDF, will allow us to work this out. So this is binomial probability distribution function. We're doing it 10 times. Chance of success is 0.4, and we're looking for the random variable being equal to 4. And we get the same answer. So please in your notes just make note that we've used binom PDF. The parameters are 10, 0.4, 4, and that was equal to this answer here. Okay, at least one patient is cured. Now there's again a couple of ways of doing this, but what we're looking for is the random variable being greater than or equal to 1, which means that what we're looking at is the random variable being equal to 1 plus the random variable equaling 2 ... plus the random variable equaling 10. All right, so that would be a lot of calculations, okay? Because you're going basically doing this with 1, doing this with 2, doing this with 3, all the way up to 10. But actually, there's a quick way to do this, and that's basically to detect that if we're looking for greater than or equal to 1, that's the probability. So that statement there is the same as 1 take away the probability of x equal 0. All right, that's a much faster way of doing this. So that will do, because we're allowed to do a 4 decimal place approximation, we'll just slam this straight out on the calculator. So what I'm going to do is binomial PDF, I'm just going to copy that across, and I'm looking for the probability that the random variable is 0, and it's that, and then we're going to do 1 take away whatever's in the answer slot. So that's going to be 0.9939940, it looks like. So yeah, that's a much faster way. Now I'm going to show you another way. Make note, please, of the things that we've done to work things out. So this is binom PDF 10 0.40. Now we could quite easily do this with the calculator as well. So the other way we can do it is by again going to probability, choosing the distributions, and choosing what's called binomial. Try again. Binomial CDF, and I think that that's a binomial cumulative distribution function. And it's a really cool function, because what it's going to do, we're going to do this 10 times. Chance of success is 0.4. What it basically says is, all right, I'm going to count up each individual random variable probabilities, like the probability that it's 1, 2, all the way up to. So you just tell me where you want me to start counting and where you want me to finish counting. So that's 1 through 10. Now, if I've done this right, this should return exactly the same answer as this one here, and it certainly does. Okay, so the other option, okay, so other opt is binom CDF 10, 0.4, and again noting that this requires one more parameter. Okay, at least 2 patients are not. So I find these ones a little bit tricky, and one way to get around the wording, because kind of what I think about is at least 2 patients are not cured. That means at most 8 patients are cured. But then I get confused with the less than and the less than and equal to's. So a way I've found to get around these ones here is to actually just define a new distribution. So we're going to go y is binomial. And we're doing the trial 10 times still. And the success is, at this time, we're going to say is not cured. Okay, so that's going to be success in this case, because that's what we're looking for this particular distribution, not cured. And then at least 2 patients are not cured means we're looking for the probability that y is greater than or equal to 2. Okay, so that means that we're looking for 2, 3, 4, or 1 take away 0 and 1. Okay, now again, for those of you who have no difficulty reversing the wording and understanding the less than and equal to's, you won't have to redefine the distribution. You'll be able to just use the original distribution. But yeah, I have a little bit of trouble with that. Okay, so I'm going to use CDF again. I'm going to change my success to 0.6, and I'm going to get it to count 2 through 10. And note that that's what I have got down there, 0. So the chance of at least 2 patients not being cured is very high. Okay, in fact, it's suggesting that the chance is 0.9983. What I try to do is make sure that that kind of makes sense in context. So a new drug is known to cure a certain illness in 40% of cases. So again, I kind of think logically, at least what's the probability of at least 2 patients not being cured? Pretty high, given that the cure rate is 40% or 0.4. So that does make sense. Okay, the last one is the invariably where the question goes to conditional. So we're looking for the probability, and we're back to cured, not cured. So we're going to use the original distribution, the x. So at least 3 patients are cured, given that the random variable is greater than 1. Okay, so we're looking for the chance that the random variable is larger than or equal to 3, given that I know it's greater than or equal to 1. So that's going to be the same as the probability that the random variable is larger than 3 over the random variable being greater than 1. So what we do is we check whether this is a subset of this, or whether this condition negates any of the things that we're looking for here, and it doesn't. So we can just go straight in and do this. All right, so we're back to the original 0.4 distribution. We're going 3 through 10 to get that one. We're going 1 through 10 to get this one here. So that's that one there. Should always, so the denominator should be higher than the numerator, so that's always a good sign. And then all I do is I copy them across. And then I note down the probability. 0.8378. So again, please note the different things that we've done on the CAS. Binom CDF, what was it? 10, 0.4, 3, 10, and this one was 1, 10. And this one was binom CDF 10, 0.6. What do we do? 210, wasn't it? Yeah. Okay, a Bernoulli trial, okay, so in other words, a binomial experiment, is conducted 5 times. The probability of success is 0.4. What is the probability of 3 successes? Work this out by hand. All right, so again, the emphasis here is that you need to be able to do this by hand or using the formula. So always define, this is probably a two-mark experiment, 2-mark question. So x is binomial, and it's being done 5 times. 2/5 is the chance for success. We're looking for the chance, probably 3 marks actually. Random variable is equal to 3, which is 5 choose 3. 2/5, we're going to see that 3 times, and 3/5, we're going to see that 2 times. So again, where am I pulling these numbers from? If you're not too familiar with it, I know you guys did binomial last year. I got it from here. That's just that formula there. Okay, so that's on your formula sheet, so you should have that out and ready to go. Okay, so how to work out 5 choose 3? Well, again, when I've marked exam 1, any time that this is being asked, I tend to find students have got, what do you call, what's his name? Pascal's triangle. 1, 5, 10, 10, 5, 1. So this is row 0, row 1, row 2, row 3, row 4, row 5. This is 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3. So 5 choose 3 is 10. Okay, so that's one way to work it out. The other way is to use the formula, which is also on the formula sheet, which is 5 factorial, 2 factorial, 3 factorial. 5 times 4 times 3 factorial over 2 times 3 factorial. See ya, 1, 2, 10. I don't know, the formula's probably a bit faster, but you got to remember the formula, or you got to look it up. Okay, so we've got 10 times 2 to the 3 over 5 to the 3 times 3 to the 2 over 5 to the 2. Okay, so this is going to be 10 times, this is going to be 2 to the 3 is 8, 3 to the 2 is 9 over, what we're going to do here is 5 to the 3 is, I'm just trying to see if I can cancel something here. I won't. So 5 to the 3 is 125, and 5 to the 2 is 25. What we'll do is we'll go 2 and we'll go 5. That's going to be then 9 8s are 72. 72 times 2 is 144. Now 5 lots of 125 is 625. So the answer should be 144 over 625. I'm going to just quickly try that on the calculator to make sure. So NCR 53 times 2 over 5 to the 3 times 3 over 5 to the 2. And you can see like that's just going to be typical exam 1. These are all calculations you need to be able to do for exam 1. So you can't be assuming that this is going to be tech active. In fact, assume that it's not. But this is a good discussion point. Why is it unlikely that you'll be asked to work out this one by hand? So we've got a trial going 12 times. So x is binomial, 12 and 0.4. And what we're looking for is the probability of at least 7 successes. Probability x greater than or equal to 7. Okay, so all looking okay so far, but what are we going to have to do? Well, we're going to have to work out the probability that the random variable is equal to 7 plus equal to 8 plus all the way up to plus x equals 12. So this one here would be 12 choose 7, 2/5 to the 7 3/5 to the 5. This one here is going to be 12, choose 8. Okay, and you can see that this is just not going to happen. I mean, like 2/5. I'm into sort of number crunching and quite enjoy it, but that one there, I've got no chance. 4, etc., etc. So this is not going to happen. That'll be a tech active question. Okay, so the final one, department store knows from experience that 65% of payments for good purchased in their store will be cash. Each transaction is independent of any other. Binomial. Find the probability of that out of 5 payments chosen at random, 1 will be cash. So 2 marks. How do you get 2 marks out of that? First mark, define your distribution. So it's binomial. With our random variable, what we're looking for is let's x equal the number of cash payments. Okay, so it's binomial. We're looking at 5 customers, and the chance of success being cash payment is 0.65. So 1 will be cash. Okay, so what we're looking for is the probability that x equals 1. Alrighty. So we're looking for the no approximation here. So I believe this will require us to use the formula. So I'm going to do 5 choose 1, 0.65 to the 1, 0.35 to the 4. Okay, so for this one, what you want to do is have your calculator either in exact mode or use fractions. So that's going to be 65 over 100 power of 1, and what's the other one? 35 over 100 power 4. Yeah. Okay, so again, we're going to write that out as a fraction because in the question, 31213 over 640, 000. In the question, it doesn't say to 4 decimal places, but again, we can check that by approximating, and then we can go and use a PDF. We're doing it 5 times, success 0.65, and the random variable value we're looking for is 1. It should give us exactly the same answer. Good. Okay, first one will be cash and the others not. Okay, so again, I added this example for this particular reason here. So this question here, a lot of students think that this will be the same. Okay, 1 will be cash, and the 1 will be cash though is it could be like cash, not cash, not cash, not cash, not cash. Could be not cash, cash, not cash, not cash, not cash. This cash could fall anywhere within the line of customers, whereas this one has a specific order. Okay, so the first one has to be cash, cash, and then it's not cash, not cash, not cash, not cash. So in fact, what we're not going to use at the moment is binomial, but we're just going to imagine the tree diagram and go, okay, so the first one is going to be cash. What's the chance of that? 0.65. And then the last 4 are not cash, so it's going to be 0.35 to the 4. Okay, so we don't get the 5 separate branches that have cash in different places. It's got to be this very specific branch. All right, so we're going to go 0.65 times 0.35 to the 4. Prefer a fraction. 31213 over 32. 1, 2, 3, 4. There we go. All right, 14A, folks. Go for it.